Hi everyone, now is our second speaker, Isabel Barrio Sanchez. She is a PhD student from the University of Pittsburgh, and her talk is New Redistribution Scheme for Weighted State Redistribution with Adaptive Match Refinement. Isa, please go ahead.
Thank you, Ray. Let me share my screen. And now I have to make this big. There we go. So thank you, Ray, and thank you for letting me talk in the seminar. As Ray mentioned, I'm a PhD student here at Pitt, and this research is something I did over the summer. I did an internship at the Berkeley lab, and so it's going to be a little different. It's a little more computational than what we used to doing here, but still very cool and very related to some of the stuff that we do here. So the name is a new re-redistribution scheme for weighted state redistribution with adaptive mesh refinement. And I worked with Anne Almgren and John Bell, which are two researchers over there. And I'm going to first motivate the problem and kind of explain for a broad audience what is it that we do when we talk about CFD, and explain the problem before I go ahead and try to talk about the algorithm. So first, well, this is my overview. I'm going to give a brief introduction to CFD. So what is CFD? Computational fluid dynamics, right? So we want to understand how fluids behave, and there are three main ways to do this: experimentally, analytically, and numerically. So the first way is experimentally, and I'm going to tell a little story. I think it's a cool story, but it's a good background. So back in the day, in the 1940s, right, we didn't have computers or any of that. And there was a guy called Reber that was from Ohio and went all the way to work in California, and he took the train. And the train left you here in Oakland. It didn't leave you in San Francisco because it couldn't cross. This is all water. This is all the bay. It couldn't cross the bay. And for that reason and other reasons, he started developing a project that was, he wanted to make two dams in the bay for two reasons. One, so that the train could cross and get to San Francisco. And another reason, which was why it was heavily supported, so that they could have fresh water. So all of this is salt water. It comes from the ocean, right? The ocean is right here. It's open. So they wanted fresh water. And the thing is, what could happen if we just make a huge dam here? And nobody knew. He had the support of many engineers, obviously the farmers, and politicians wanted these two because it gives fresh water, but nobody really knew if this was possible. So it got to Congress, and Congress gave him $2.5 million. Well, not him. Congress gave the Army Corps of Engineers $2.5 million, which nowadays is not that much, but in the 1940s, it was a lot of money, to see whether this was possible. And what the Army Corps of Engineers was this thing to the right. It's a huge experiment. They just made a mini bay area here. It's on some building, and they tested a bunch of experiments. They created dams in different ways to see whether this was possible. And well, at the end, they decided it was not possible. In the winter, there was too much water. It was gonna overflow. They can test this with like high tides and low tides and more water or less water. And they said, well, we shouldn't go forward with this. So that's why there's not a big dam in the Bay Area. So this is a way to study flows, right? We just make a huge experiment. However, this is not very scalable, and it is very expensive. So if we wanted to see, well, I want to build a dam here now in the Allegheny River, I don't know, I can't use this model. I have to use something different. So the second way is analytically, right? We have these equations that model how fluids move, and if we solve them, then, right, we have our solution. But these equations are hard to solve, or maybe our domains are very weird, or they're changing. And so this is also not possible. So then computers came to help, and that's what we do with CFD. And this image is underwhelming compared to the other ones. But so imagine this blue thing is a river, and the gray in the middle is a rock, and we want to see how the fluid moves around that rock. So imagine it's moving this way. And we don't want to create an experiment. What we can do is try to solve those problems, those equations that are hard to solve, but we approximate them. So those equations are differential equations. we can approximate derivatives, right? Remember in Calc 1, we want to approximate the derivative at a point. We can take 2 points close to that point, draw a line among them, and that's almost the slope of a tangent line. And the closer those 2 points are, the better our approximation is. It's the same thing. We make a discretization of our domain, and the smaller the squares are, the better our approximation will be. And we just let the computers do the job for us. Obviously, in the 40s, they didn't have this technology. These days, we do this all the time. So there's many different ways to discretize things. There's many different methods that we can use to approximate these equations, and there's many different ways that we can deal with these solids that are in the middle of the fluid. And we used one of them, and that's what I'm going to explain. So it's the single level algorithm. We'll see what that is later. But we're going to use embedded boundary methods. So imagine this is part of my rock that I had on the previous slide. The orange is the rock, the white is the fluid. First, we don't like curves. We would like to have straight lines because each of these, I want the normal vector to this line. So one thing we can do, and this is what the embedded boundary methods do, is just take the intersection of these 2 points with the grid, draw a straight line, and this is close enough, right? If our square is small enough, this will be like, we can say good enough. The error won't be too big. And one thing I have to say, we have been working with what are called structured grids, which are just what we think of when we think of a grid. So we can go from here. This is ij, then this would be I plus 1, j, this would be I, j plus 1. It has an order. So there's other methods that use unstructured grids, but for our purposes here, we use structured grids. And another thing I want to talk about is the finite volume schemes in general. So there's finite element schemes, finite difference. We're using finite volume. So for example, we have these system of hyperbolic conservation laws. So derivative of your conserved quantity with respect to time, and then f is the flux, and this is a vector. So imagine we're working in 3 dimensions, the flux in x, in y, and in z. We can integrate this, and here we can take the derivative out, and here we use divergence theorem, and we get rid of this derivative when we use divergence theorem, and now we have the integral over the boundary. And now if we let u hat be the average value of u over v. V, we can think about each of these squares, we can call it one. Each of those is a v. We'll do that later. So the average value of a function over a certain domain, that's the equation. So we can rewrite this equation with the u hats as the derivative of the u hat. We would get an extra volume here. We divide by it on the other side, and I take the f's to the other side, and that's how I get this equation. And now I can approximate these derivatives in time, and that's what I'm doing here. U hat n plus 1 minus u hat n divided by delta t, and I haven't done anything with this yet. And now it's like abusive notation, but notation, whatever you want to call it. Now my u hats have turned into u's. From now on, these are the same thing. So every time I refer to as u or un plus 1, it's the quantity. It is the average quantity over each of those cells, each of those volumes. So that's what finite volume schemes do. They compute an average value over each of those cells or each of those volumes. So now these u's are these u hats, but I'm not going to write the hats. Multiply by delta t, right? And I have these delta uc. There's many ways to deal with these fluxes. That's a whole nother topic. I'm just gonna leave this here. One thing I do want to mention is Vijk is the volume fraction of each cell. What does that mean? So not all cells have fluid in it. For example, the volume fraction of this cell that's fully orange is 0. The volume fraction of this cell will be very small, for example, 0.1. So lambda is how much of each cell is fluid. So in this case, imagine lambda is 0.1. So V will be weighted with how big the cell is. So for example, if each cell is a 2 by 2, then this would be 0.1 times 2 by 2 by 2. So this just represents the amount of cell that is not covered by your solid. So rewriting that above, but I didn't want to write the delta U's. We have UN plus 1 equals UN plus this delta T divided by V times some stuff. And there's this thing called the CFL condition that tells you how big your T can be, your delta T can be, so that your method is stable. And normally when you're not using embedded boundary methods, it depends on the width of your mesh. Now here we have to care about also how much of the cell is not covered, how much of it does actually have fluid. So basically your delta T depends linearly on your V. Now, what is the problem here? We're just taking a problem, we're taking a solid, we're putting a grid on top of it. And so the amount of cell that is not covered can be arbitrarily small. So that means that my delta T can be arbitrarily small, and that is just very computationally expensive. Well, it's like arbitrarily expensive. We don't want that. So that is the small cell problem, and we have to do something about it. And that is one of the two problems that I will mention today. The good news is there is ways to deal with this small cell problem. We were using weighted state redistribution, which is an algorithm that was developed by the people that I was working with, Anne and John, and their collaborators. And the main idea, I'm not going to go into it in detail because it's a lot of bookkeeping, but you can merge these small cells with neighboring cells. So for example, this cell is very small. I merge it with this top cell in that direction of the normal. And you can specify what is too small for you. So for us, it was the volume of a normal cell divided by 2. If a cell is smaller than that, we're going to merge it. For example, cell 3 doesn't get merged because it's big enough. And so you have to keep track for each cell. Now instead of cells, you have neighborhoods. So this green thing is a neighborhood. You have to keep track which cells are in each neighborhood, and for each cell, what neighborhoods it's in. So for example, this cell in the middle, cell 3, is in its own neighborhood, but it's also on this one's neighborhood. So you have to keep track of a lot of things. But to shorten it, you compute for each cell some weighted volumes, so volume of the cell, and keeping track of how much each cell is contributing to the neighborhood, and some weighted solution averages. And the algorithm can be, at the end, expressed in matrix form. Say this is your final update, it's a vector. UN plus 1 is A transpose Q hat, where A is a matrix, such that V hat equals AB. V hat is the weighted volumes. So that is, we've solved the first problem, right? We haven't done anything. Now, it's just for one level. So remember how I said the smaller the mesh, the more accurate that our solution is going to be. Now, we could just refine everything, make a small mesh, but then our computer is just going to give up on us and we're not going to be able to solve anything. So one thing we can do is imagine this is just like a big river. Nothing's happening up here. Nothing's happening up here, but here there's a few rocks. So I want to see what's happening like close to the rocks, right? Everywhere else, it's not that interesting. The flow is not going to change as much, so I don't need that much refinement. So what I can do is just refine it there, and I can have multiple levels of refinement. So for example, the black one is level 0, the blue one's level 1, the red one's level 2. I can keep doing this. So the way we do it with, and it's called adaptive, because we can just specify, well, if this happens, then make a smaller grid. You can just put that into the code. And one thing that comes up is we first compute things in the coarse grid. We advance the coarse grid, and then we advance this blue grid and then this red grid. But we advance the levels independently of each other. So this leads to a problem, which is that the flux at the boundary, from now on, I'm going to call this a coarse fine boundary because it's the boundary between the coarse mesh and the fine mesh. These fluxes don't necessarily match, and that's a problem because I'm going to use the fluxes for this cell that are computed on this phase, and also compute the fluxes for this cell that are computed on this phase, and they should match, but they don't. So we need to do something about it, and what we do, it's called refluxing. There's a lot of words. Basically, we just take the average of the fluxes on the fine grid and go with it, substitute it. So use the solution on the fine grid. So I just want to like stop here and say this is what we had. We had the small cell problem. We solved it with redistribution. And then we had the flux problem, and we solved it with refluxing. So now it's when the project started. And the question is, what if we have an embedded boundary, that is, what if we have a solid and a small cell that is close to the coarse fine boundary, that is close to this fine mesh? Then it might happen that both problems come together in the same cell, and we have not done anything about it. So up until a couple months ago, you could not do this with weighted state redistribution. So basically, there's you have to redistribute the reflux and reflux the redistribution, and that's what the algorithm is called, re-redistribution. So when you were doing reflux and computing the flux at the edge, you need to redistribute that amount if it is in a cell that's a small cell. And also when we were doing redistribution, I'm gonna go back to this slide. Imagine this is a fine grid and this is a coarse grid. There's a boundary here. Then when we were computing these weighted solution averages, we took updates from this cell into this cell, but that is also crossing a coarse fine boundary, so it should be computed into the flux. So we need to reflux the redistribution. So that's what we mean by that. Now, how do we reflux? First, we reflux the redistribution. So this is just notation for what we call a cell. So the blue grid is the coarse grid, the red grid is a fine grid. So uncovered coarse cell is these two. It's a blue cell that's not covered by a red cell. Covered coarse cell are these blue cells that are below a fine cell. And then we have valid fine cells, which are just the fine cells as we were thinking of before now. But we also have to have ghost cells, because these fine cells are ghost cells hold information, basically store information from these fine cells. So we just needed them to store information. And when we do redistribution, there's information that was passed between covered coarse cells to uncovered coarse cells and vice versa. Some of it we need to still keep track of, and some of we need to get rid of, because now we have to update our solution with the fine grid. And similarly, we have fine ghost cells selling information to valid fine cells and vice versa that we need to keep track of. And we store these quantities as delta R's for each cell and for each level. So this L is the level. So for example, blue level is level 0 and red level is level 1, and IJK is the cell. And I haven't added this into here, but the way we compute these delta R's, remember how before I had that we can write the weighted state redistribution as a matrix. We can do something similar to weighted state redistribution. We need to keep track of what cell gives stuff to which other cells. It's just a lot of bookkeeping and seeing when are things actually happening. And we can do that and store that into a matrix. And then these delta R's will be the sum of the rows or the sum of the columns. And I have to say those matrices are sparse in general. So that's not too bad. And it's just a matter of keeping track of what's happening. And now we have to redistribute the reflux. This is not the same redistribution as before. So now we have to update its cell at each level, and we can update it like this with the delta R's that we computed before when we were refluxing the redistribution. Now, again, we're dividing by V. V might be very small. This might introduce an instability. And so we need to redistribute or do something about this quantity, and we call this redistribute. So what we do is we multiply by this lambda. If we multiply by lambda, remember V was lambda times delta X, delta Y, delta Z, then we will just get 1 over delta X, delta Y, delta Z. That can't be arbitrarily small, that is stable. So we do this update and we redistribute the remainder from here to here to neighboring cells. So that is what we mean by redistributing the reflux. And that's basically the algorithm. If you're interested about like the details of the algorithm, you can talk to me, or I'll also have the paper has the same name as a talk. You can look it up, it's our archive. And then we ran some numerical examples. So this is the first example we ran. Well, first we ran like a sod shock tube like this, but completely flat, just to debug the code. But then we run this. This is a 30-degree angle. And so in this case, our embedded, so these are walls, and then there's fluid with high density and high pressure here, and then low density and low pressure here. And there's a wall in the middle at time 0. And here, the embedded boundary, right? This is the solid, these are the walls. There will be an embedded boundary here. So all these cells at the intersection, some of them will be small cells. And then we refine just one level. And you can see the smallest cells here. And when you let it run, at time equals 0.4, now we see what happens. And then to test, because the reason why we ran this is because we have an analytic solution to this problem. We ran it after this with the shock perpendicular to the walls, and this is what we got. So the exact solution is this dashed line for each density, pressure, velocity, and temperature. So, and then we just use different spacings. And we can see our solution is pretty good. We see the shock, we see the refraction rate wave. So that was the first problem that we ran. This was just in 2D. We also ran in 3D, but these are solutions for 2D. We ran another experiment that's flowed past the cylinder. So we create a shock wave here. So low density one side, high density on another side. And we let the shock go this way to the right. And this white cylinder is a solid. So when it approaches, it's going to push air in this direction, right? So this area over here, as we can see, is going to have high pressure and high density. And so we ran it first, refining everywhere. So if you refine everywhere, you're not really using our algorithm because the coarse line boundary is not crossing the embedded boundary. And then we refined just half of the circle so that we could have that coarse line boundary intersecting the embedded boundary. And obviously the solution is going to be better because it's more refined, but this problem is symmetric. You don't really need to do it on both sides. So if we compare the time that each one took to run, ours took way less time. And we can compare this to, I think this is just a cool picture. You can actually run the experiment for this problem, like run actually experiment in a lab and take, this is called a Schlieren photograph. I don't know how they take photographs of shocks, but it's something you can do. And we compared it to our simulation. We can see it looks very similar. And yep, then we also ran a test in 3D. I haven't added it here. But you can use this algorithm both for 2D and 3D. And the last thing I want to mention is this algorithm is in something called AMR-X, is huge package to run parallel block structured AMR applications. And yeah, a lot of people use it at the labs, and we just added this algorithm. So in case I wanted to use it, you can just run it with that. And that's it. These are the references. And thank you. And I'll take questions now if there's any.
Thank you, Isa, for the awesome talk.